Hey, good morning. This is Mr. Arnold, and today we're going to finish up this nuclear chemistry with the last section. It's a very, very short section, so there'll be another thing this week. This will be very short, I promise. Nuclear fusion. We're going to go back and start about just quick talk about what fission was. Fission was the splitting of the atom, and the reason it released energy was because after it split apart, the parts that it split into had less mass than the original. And that goes back to E equals mc squared, where the mass difference, or that nuclear mass defect times the speed of light squared, equals the energy released in a nuclear reaction. So that's how that works in fission. So it's splitting that way. So the differences between the two nuclei, or the two nuclei and the pieces parts, are lighter than the original. Okay, now let's look at this chart. This chart is kind of weird, and it might take a little bit to get the gist of this. But when you have small particles all the way up until you get to iron, right? The mass changes as you join them together. And so the mass changes a lot more when they're smaller particles. After you get to iron, it kind of reverses, where the size or the mass of the particles start going back up. And we're talking about the subatomic particles, right? And so then the mass changes again. All right, so what this means for us is in fission, and this would be the fission side here, the larger atoms that are splitting apart, if they do split apart, not everything does split apart, right? But if they do split apart, this would be the size of the different particles as they break apart. So if you had a big uranium nucleus and it broke into two smaller nucleuses, that it does, I'm just making up the spots, right? And it broke into two smaller nucleuses. Those two smaller nucleuses would have less mass than the original uranium. And so that's why it gave. All right, so as the larger nucleuses split apart, they have less mass of each individual particle. So they're losing that mass, it's turning into energy. Well, for fusion, the opposite happens. As the smaller nucleuses join together, they lose mass. So by joining together, they lose mass. On this side of the dotted line, let's put that in some kind of highlight. And on the other side, they lose mass if they were split apart. Now, this is where we have to look at the curves. This curve on this side is humongously steep. That means it creates a lot more energy, especially for those helium or hydrogen to helium formation, right? That's a huge amount of energy produced. And so when we talk about fusion, it's going to create a huge amount of energy compared to what the fission reaction was. Oops, okay. So let's see how this is our reactions. This is just a basic fusion reaction. If they could do a fusion reaction and control it on Earth, this is what they would do. Now, this is deuterium. Deuterium is just hydrogen that has an extra neutron, right? So I'm looking right here. So we have two deuteriums, and they have to get these things hot enough and moving so fast that they can overcome those positive forces and slam together and become something else. And once it does, it becomes a helium isotope that has only one neutron. All right? And then it gives off an extra neutron. All right? So it just forms into a helium, a lighter helium, but still a helium. Another version would have a deuterium and a trillium. And when they were fused together, then they would form just a normal helium and an extra neutron. So both of these things, the byproduct is a neutron and a helium, and none of those things are really radioactive. So there's no pollution produced. And in return, it produces huge amounts of energy. so much more than fission. The fusion reaction of the isotopes, blah blah blah. So, you know, to do this though, it has to be really, really, really hot. Right, super hot, hotter than, and I'll talk about this in a little bit, but hotter than the containers that we can make. This happens in the sun. This happens in the stars. It produces huge amounts of energy, and we'll talk about that in a second. Okay, so let's see, did I skip anything? No. After fusion, the total mass of the nuclei is less than the total mass that was before, and that's what we talked about. That missing mass equals mc squared. That's where the energy comes from, right? And it has to go so fast to do this. Now we call this thermonuclear fusion, right? So thermo is heat, nuclear fusion, and that means that we have to be very hot, and that means they have to move very fast, right? Because temperature is the average kinetic energy of the particles, and they have to go really fast. They have to be super hot temperatures. And I'm going to talk about this right now. It's kind of jumping ahead, but to do this and produce infusion, I'm one step up there. See, it has to be so hot that there's no materials that would be left. They would all melt and vaporize. So they don't have a container that can hold this, a physical container that can hold a fusion reaction, because the container would vaporize and turn into plasma. Plasma is the high energy state of matter, right? It would turn into the plasma also and disintegrate and vaporize and be gone. All right. Here's just a thing. This is our sun. There's 657 million tons of hydrogen converted into 653 million tons of helium per second. Okay, now those numbers don't match up, right? And the reason is because that other mass is then lost to energy. It becomes energy equals mc squared. And so 4 million tons of mass turns into energy. So just times that by the speed of light squared, and you can see that's a lot of energy produced. That's per second. Okay, so the sun is losing 4 tons of mass per second, all being converted into energy. Now, the solution to this is the magnetic, not the magic bottle, the magnetic bottle. The only way they can have a fusion on Earth, and we're not talking about the hydrogen bomb, because that also is fusion on Earth, but that's not contained. We'll say it this way: they can have contained fusion on Earth is to have a magnetic bottle. The plasma is so excited. It's excited and moving so fast, but it still has its magnetic movement because it's charged particles moving around, right? And so a magnetic field can contain that and hold it, and it can even squeeze it. And so just like in the gas laws, if you squeeze the pressure together, it gets hotter. The same thing happens here. They squeeze it together because it's not a gas, it's plasma, but it's follows the same rules there. They squeeze it in and it even becomes hotter, increasing the temperature. But it's still hard to get enough, it's still hard to get it going fast enough to fuse, even with this magnetic bottle. And so they have this thing where they try to shoot lasers in there and try to heat them up even more. But it's, at this point right now, they cannot produce more energy than what it takes to get this thing contained and get the particles moving fast enough to even fuse. So right now it's a negative energy outcome, right? They can't get it going. They can't get it self-contained where the fusion will just go on by itself, because they got to keep sending particles in. They got to keep applying energy to contain it. They just can't keep it self-contained like it is in the sun. They just haven't figured it out yet. So that's a reason we can't do fusion on Earth as a power source right now. So, well, scientists all over the world are working on this. I mean, there's huge coalitions made between different countries trying to work together and get this fusion going, because it would be a game changer in the whole entire Earth, right? It would be unlimited energy from common everyday things. You could take, well, let's say just hydrogen alone. There's enough hydrogen. I thought I had that on here. Oh, here it is. There's enough hydrogen in the earth because we have all that water, right? Hydrogen is the most common element in the universe, right? And so we have plenty of hydrogen on Earth. We have a whole ocean full of H2O, right? And then there's deuterium. Deuterium is that hydrogen with the extra proton. And there is plenty of that in there too. And tritium, there's not as much as that, but if you have a nuclear reactor and then they're using the water nuclear reactor, the heavy water nuclear reactor, it makes tritium. It excites those hydrogen atoms in the water, and it actually forms tritium, so they can make that. So there will be plenty of fuel, and the byproduct is only helium. But I'm surely not following this pattern, am I? Is only helium. So there's nothing that's radioactive. There's maybe in the core it would be radioactive for a short period of time, but that's not very much space there, and it's not like it's going to be an extra lot of fuel, right? And it would be unlimited energy, a fuel that is easy to get and plentiful, and there is no chance that a fusion reaction in this way would go supercritical and accidentally explode. When they do those fusion reactions for the hydrogen bombs, it explodes, but they do that. It's not, they're not trying to control it. They're putting that much energy in there and doing it all at one time. So it's not like it would be supercritical for that. Okay. And that's pretty much for this section. So I just had some quick questions I made up. There wasn't much I could do for this section. So I am going to come back, and I am going to have another section this week, but I'm going to do it different. I found an interesting chapter in one of the books, and I just copied the book, and we're just going to do the questions out of that. And I'll probably either put that up today or tomorrow. And I'll have like a one section, and then we'll do the other sections as the week goes on. So that's it for this section, and this will be 7.2. And all you need is those 4 questions. All right, have a great day, and I will be in contact later this week, and figure out what I'm going to do with this next chapter. You know, I keep changing my mind what I want to do. I will let you know.